Traditional paper currency is fragile. As a blend of cotton and linen, it absorbs moisture, traps grease, and physically degrades, passing hand to hand, $1 billion over 25 years. The unit economics of this shift are significant. A single polymer note costs the Reserve Bank about 25 cents to print. By comparison, an upgraded paper note costs just 13 cents. Because the upfront manufacturing cost of plastic is double that of paper, a polymer bill must survive in circulation significantly more than twice as long to become a net positive. Polymer's physical properties make that longevity likely. The substrate is non-porous and water-resistant, virtually immune to the dirt and grease that destroy traditional paper. This physical superiority leads most to assume that upgrading to longer-lasting money is a cheaper option for every denomination in a currency series. After 25 years, the Reserve Bank conducted a cost-benefit analysis to verify if the transition to polymer actually worked across the board. This chart tracks inflation-adjusted savings for each individual denomination since the switch. The lower denominations, the $5, $10, and $20 notes, achieved positive net savings within 4 years. However, the data reveals a massive anomaly. The transition of the $100 note resulted in a substantial net financial loss. Curious, despite being printed on the same durable material as the others, the $100 bill failed to break even. This raises a central mystery. If polymer is physically superior, why did engineering an indestructible high-denomination bill create a financial liability for the central bank? To find the answer, we look at the first variable of the framework, initial migration cost. Transitioning a currency requires printing an entirely new circulating supply all at once. This creates an immediate and massive capital expenditure. Central banks must also print a contingency buffer, usually a full year's demand, to prevent sudden liquidity crises if production is ever disrupted. Then there is the logistical cost of the recall. The central bank must securely retrieve, process, and destroy every bill in the old paper series. Processing and destroying those notes cost roughly 10 cents per unit, adding millions in sunk costs to the transition. This immense upfront cost puts a central bank in a deep financial deficit. They must then wait for long-term savings to slowly claw back that initial investment. That recovery depends on the second half of the framework, annual replacement savings. Savings only accrue when a note physically fails and requires a replacement. The bank saves money when a polymer note survives a situation that would have ruined a paper bill. The rate of these savings is dictated by a metric called transactional velocity. Low-denomination notes like the 5 and 10 have incredibly high transactional velocity. Because of that friction, paper versions were destroyed in under a year. Upgrading to polymer slashed the replacement rate, helping the bank reach break-even in just 4 years. But high-denomination notes like the $100 bill operate under different behavioral economics. The $100 note is a store of value. It is hoarded in safes and under mattresses, rarely entering active circulation. Because a paper $100 note rarely experiences friction, it almost never physically degrades. Even the cotton linen versions lasted for years without needing to be replaced. Without a high replacement rate, the central bank never realizes the ongoing operational savings needed to offset that massive migration cost. For hoarded denominations, the central bank simply paid double the unit cost for durability it didn't need. Polymer's financial value is entirely dependent on the behavioral velocity of the cash. One might assume that if polymer can physically last 50 years, a hoarded $100 note will eventually break even if given enough time. However, modern currency has a hard limit, the counterfeiting cycle. Central banks cannot leave a series in circulation indefinitely. To stay ahead of imaging technology and fraudsters, central banks must upgrade currency security features every 10 to 15 years. These upgrades carry a long-term impact on savings, requiring a new migration cost every decade or two. This creates a jagged sawtooth pattern in the data. The forced recall of perfectly good polymer every 15 years creates massive expenditure spikes that drop net savings downward. These forced upgrades also involve logistical friction. The Central Bank of Nigeria, for example, experienced significant difficulties safely destroying retired polymer compared to paper. Technological obsolescence serves as the true expiration date for a banknote, capping the economic potential of indestructible substrates.